Hello, my name is Shivansh and I'll be reviewing transformations, radicals, and polynomials. Okay, so the first question we'll be doing is polynomials. Let's start off with an easier question here. We've got this cubic polynomial, x cubed minus 6x squared plus 11x minus 6. Now, the first thing we're going to do is look at the constant term 6 here, and we're going to find all the factors of 6. So, factors of 6 are plus or minus 1, plus minus 2, plus minus 3, and plus minus 6. So let's try, for example, let's try x equals 1 as a test point. X equals 1. Let's plug in 1. Because our goal is for whatever x value we put in here, the p of x should end up equaling 0. That's how we know that the x value is a root of the function. So p of 1 cubed minus 6 times 1 squared plus 11 times 1 minus 6, which ends up being 1 minus 6 plus 11 minus 6. So 1 minus 6, negative 5 plus 11, positive 6 minus 6 equals 0. So now that this does equal 0, we know that therefore x equals 1 is a root, and that means x minus 1 is a factor of this polynomial. Now that we have this, we can use synthetic division. With synthetic division, we'll use this x equals 1 point again. We'll use 1, set up our division. And for synthetic division, what we use is only the coefficients, not the variables. So we'll write down 1 for the x cubed, minus 6 plus 11, and then minus 6 again. Now we start off, bring our 1 down, 1. 1 times 1 is 1, bring it here. Negative 6 plus 1 is negative 5. Bring the negative 5 times 1, negative 5. 11 plus negative 5 is positive 6. 6 times 1 is 6. Negative 6 plus 6 is 0. Now with synthetic division, after we divide, we go down 1 for the degree of the function. So the degree of this function is 3. Now that we've divided, the degree of the function is now 2. So it ends up being x squared minus 5x plus 6. Now with this one, there are multiple ways of figuring out the roots of this function. We can graph, we can do by inspection, we can do by decomposition. The way I'll do it is by graphing. So I'll pull out my calculator. Let's plug in x squared minus 5x plus 6 and press graph. Now let's adjust our window a little bit here. Okay, so now to find the roots on our graphing calculator, we go second function, trace 0. Then for the first point, we go left bound. So let's try and find this point here. We'll go guess there, right bound, just put something there, and then a guess around there. And our 0 is x equals 2. So one of the zeros of this function is x minus 2. Now the second one, we'll do the same process. We'll go left bound here, right bound there, and a small guess in between. We get x equals 3. So x minus 3. These are the factors of x squared plus 5x minus 6, which also makes them the factors of this. So now we take this x minus 1, take this x minus 2, x minus 3, and put them all together. Our final equation should be p of x equals x minus 1, x minus 2, x minus 3. So here I have another polynomials question. This question is k to the power of 5 plus 3k to the power of 4 minus 5k to the power of 3 minus 15k squared plus 4k plus 12. Now to solve this, it's the same as usual. First we do is we look at our constant value 12 and we list out all the factors. So the factors of 12 are plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, and plus or minus 12. Out of all of these, we choose a test point to plug into this and synthetically divide. The first point I'm going to use is k equals 1. So if k equals 1 ends up being valid and the remainder after doing synthetic division is 0, then I know that k equals 1 is a valid root of this equation. So here I have my synthetic division set up. These coefficients here are the coefficients of the k terms in this equation. So first we do is bring down the 1. 1 times 1 is 1. Bring it over here. 3 plus 1 is 4. 4 times 1 is 4. Negative 5 plus 4 is negative 1. Negative 1 times 1 is negative 1. Negative 15 plus negative 1 is negative 16. Negative 16 times 1 is negative 16. 4 plus negative 16 is negative 12. Negative 12 times 1 is negative 12. 12 plus negative 12 is 0. So that way we know that this is a valid point, which means k equals 1 is a root and k minus 1 is a factor. Now, after synthetically dividing, the degree of this function goes down by 1. So from 5th degree, it goes down to a 4th degree. Instead of factoring a 4th degree, I'm going to do synthetic division again to make it into a 3rd degree, then a 2nd degree. That's the easier way to do this. So for this next one, I think I'm going to choose k equals negative 1. Well, so we're going to set up the same synthetic division as before, only with this new equation now. So 1, bring it down. 1 times 1 is negative 1. 4 plus negative 1 is 3. 3 times negative 1 is negative 3. Negative 1 plus negative 3 is negative 4. Negative 4 times negative 1 is positive 4. Negative 16 plus 4 is negative 12. Negative 12 times negative 1 is positive 12. Negative 12 plus 12 is 0, which means that k equals negative 1 is also a valid root, and k plus 1 therefore is also a valid factor. Now we've gone down one more in degree, so that means we have a cubic function here, k cubed plus 3k squared minus 4k minus 12. We're going to go through synthetic division one more time and turn it into a quadratic. This time I'm going to use the point k equals 2. So here's my synthetic division setup. We bring our 1 down, it becomes 1. 1 times 2 is 2. 3 plus 2 is 5. 5 times 2 is 10. Negative 4 plus 10 is 6. 6 times 2 is 12. Negative 12 plus 12 is 0. Therefore, k equals 2 is a valid root and k minus 2 is a valid factor. Now we have this quadratic function. We could factor this by graphing, by decomposing, inspection, any way you prefer. I've got the factors here from graphing, k plus 3 and k plus 2. Now to find the final equation, we take all of these factors that we figured out here and we just put them all together. So our final equation is p of k equals k minus 1, k plus 1, k minus 2, k plus 2, and k plus 3. Okay, let's do a transformations question here. This question says, consider the graph of y equals f of x. Sketch the graph of each transformation. So here's our graph and here's a transformation. So here we've got y equals 1/2 f of negative x plus 2. So how I would approach this question is first I think about the acronym SRT. Stretches, reflections, translations. Every time you look at a transformation question, you should do it in this exact order. So first, let's look for stretches. Let's see. We've got a vertical stretch here by a factor of 1/2, and that seems to be all. So stretches, vertical stretch by a factor of 1/2 about the x-axis. Are there any more stretches? No, there are not. So now we can move on to reflections. Now with reflections, if we notice that the negative sign is within the brackets, that means we've got a horizontal reflection. If the negative sign is on the outside, we've got a vertical reflection. Here we've got a horizontal reflection in the y-axis. Are there any more reflections? No, there are not, which means we can now move on to the final part, translations. Now translations, we can see that there's one translation here. We've got a horizontal shift 2 units to the left. Now let's describe what's going on in this in mapping notation. So for this one, for stretches, the point xy turns into the point x and 1/2 y. We're changing the y value. For reflections, the horizontal reflection means we turn point xy into the point -x and y. Now the final part, translations, this horizontal shift means we turn the point xy into the point x minus 2y. Now let's combine all of these into one big mapping notation. Point xy becomes -x minus 2 and 1/2 y. Now let's graph this new function with the information we presented. So I've labeled out some key points on the graph of f of x. We've got 3, 2, 2, 3, 4, 3, 1, 6, and 5, 6. So let's apply these stretches, reflections, and translations and figure out the new points. So for 3, 2, we're going to apply the stretches. Now the stretches affect the y value. So 2 times 1/2 is 1. So this becomes 3, 1. Then we apply the reflections. Now the reflection states that the point xy turns into -xy, which means we have -3 and 1. Now the point -3 and 1, we apply the translation. The translation shows that we're going 2 units to the left. So this becomes -5 and 1. Now let's do the same thing for this next point. 2, 3, we apply the stretch. 3 times 1/2, we have 2 and 3 over 2. Then we apply the reflection, we get -2 and 3 over 2. Then we add the translation, which makes it -4 and 3 over 2. Now for 3, we have the stretch first. 3 times 1/2 makes it 4 and 3 over 2. Then we apply the reflection, which switches the x value, -4 and 3 over 2. Then we apply the translation last. We get 2 units to the left, so we get -6 and 3 over 2. Now for 1, 6, the stretch, 1 over 6 times 1/2 becomes 1 and 3. Then we apply the reflection, we get -1 and 3. Then we apply the translation, we get -3 and 3. Now for the final one, apply the stretch first. 6 times 1/2 becomes 3, 5 and 3. Then we apply the reflection, we get -5 and 3. Then we apply the translation, we get -7 and 3. Now we take all these new points and we'll plot it on the new graph. So I'll just do that in a separate color so you can see. -5 is here in the middle and 1 is right there. -4 is right here. 3 over 2 is 1.5, so we'll just bring it up a little bit right there. -6 is right here. 3 over 2 is 1.5, so we'll just bring it right there. Negative 3 is here in the middle, and then we'll bring it up to 3. Negative 7 is over here in the middle, and we'll bring it up to 3. There's our points. Now if we just draw our new graph, we've got the transform graph y equals 1/2 f of negative x plus 2. Here we've got another transformations question. This question says, the graph of the function f of x equals absolute value of x is transformed to the graph of g of x equals f of x plus 2 minus 7. We're going to go over these 4 points, starting with part A. It's asking, describe the transformation. When we're describing transformations, we're going to look at the parameters. These parameters are the values a, b, h, and k, because this g of x function is in this form. G of x equals a times f inside b x minus h plus k, where we're trying to find out the a, b, h, and k values. So the a value here is 1. The b value here is 1. So this tells us that there's no vertical or horizontal stretches. The h value here is negative 2. And the k value is negative 7. So this tells us that there are only horizontal and vertical shifts. So we've got a horizontal shift, 2 units left. And we've got a vertical shift, 7 units down. Now in mapping notation, the point xy turns into the point x minus 2 and y minus 7. Now, moving on to part B. Part B is asking about the equation of the function g of x. So, we have f of x equals absolute value of x. We're going to just plug in, instead of x, we're going to plug in x plus 2, and instead of the y, we're just going to put y minus 7. So g of x equals absolute value of x plus 2 minus 7. And that's the equation of g of x. Now we move on to part C. Determine the minimum value of g of x. So we're just going to apply these translations onto the minimum value of f of x. So in an absolute value function, the minimum value is 0, 0. And we're going to apply this mapping notation translations to 0, 0. So 0 minus 2 and 0 minus 7, which ends up being negative 2, negative 7. Therefore, the minimum value on the graph of g of x is negative 2 and negative 7. Now let's move on to part D. Part D isn't much math, but it's more explaining. The domain of the function f of x is the set of real numbers. The domain of the function g of x is also the set of real numbers. Does this imply that all the points are invariant? Explain your answer. Well, the domain is set for real numbers of f of x and g of x because we can plug in any number value for x. So let's just write that. So we can plug in any real number value for x into both of these and they will be defined. But there aren't any invariant points because g of x went underneath some translations here. It underwent some translations. It went 2 units left and 7 units down. Went through translations. all points on f of x have now been shifted 2 units to the left and 7 units down. So they all have new coordinates. So there aren't any points on f of x that have stayed the same upon the horizontal and vertical translation.
Okay, so here we have a question
which
regarding
means that all of
radical
the points
functions
are
and the square root of a
non-invariant.
function.
So this question says, using each graph of f of x, sketch the graph of square root f of x. Here we're given f of x, it's a straight line, and now we're supposed to sketch the square root. Now with square root functions, when a function is square rooted, we only square root the y values. So we don't pay much attention to the x values, they're not really much importance because the x values will stay the same. And also, when you're drawing the square root of a function, your function should always be above the x-axis because the square root of a negative is a non-real answer. So we can't really plot that on a graph. So in mapping notation, what I'm saying here is the point xy turns into the point x and square root y. Now, there's also invariant points. Invariant points occur at y equals 0 and y equals 1. This is because when we square root 0 or square root 1, they end up being 0 and 1. So for example, x and 0, square root of 0 is still 0, so that stays the same for both graphs. Same with 1. If x and 1 on the original f of x graph, and then we square root it, x and square root of 1, we get the same value. These are invariant points. Invariant points. Now, invariant points aside, let's test out some points on this graph. So I see 2 and 1. I see 3 and 3. Let's start off with those. Let's see, 2 and 1. Put a square root on the y value, becomes 2 and square root 1. Which is still 2 and 1. So 2 and 1 is invariant. It'll be on both graphs. Next, let's try 3 and 3. 3 square root 3. Square root of 3 is around 1.7. So let's do 3. Square root of 3 right there. 1.732. 1.732. So on the new square root graph, we will have 2 and 1 and 3 and 1.732. Next, I wanted to talk about what else you'll see on the square root function. So for example, if we had a point x and 0.5, 0.5 is less than 1. When you square root 0.5, you will get a greater value. Square root 0.5. We get 0.71, which is greater than 0.5. Whereas if a y value is greater than 1, then your square root value ends up being less than the original. So x and square root 0.5 ends up being x and 0.71. So beware of that when we're graphing, because I'll show you when we're graphing how that applies. Next, let's see some other points. Let's see this x-intercept here. The x-intercept is on the line y equals 0, so we should see it be invariant. 1.5 and 0 turns into 1.5 and square root 0, which ends up being the exact same point. So 1.5 and 0 is still invariant. So far we got this point and this point both being invariant. Next, let's try some points where we don't need to pay attention to the x value. Let's say x and wherever y is equal to 2. Let's square root 2. square root 2. We get 1.41-ish. And then let's try x and 4. See wherever y is equal to 4 around there, so we don't really need to pay much attention to x value. Square root of 4 is 2, so now on the square root function, it will be x and 2. Now that we've got a couple test points here, let's put this on a graph. So on the graph, let's see. We've got 2 and 1 being invariant, and we've got 1.5 and 0 being invariant. These 2 points stay the same on both graphs. Now, anything here less than 1.5, let's say 1, will be behind this line. So when we're graphing this, we put a very small little curve here to show that it's greater. And after it passes this 2, 1, it continues on being smaller and smaller and smaller than the original y value. So let's make sure we get this right. It should be something that looks approximately like this. This would be y equals square root f of x. So here we have another radical functions question. This question says, if negative 2412 is a point on the graph of the function y equals f of x, identify one point on the graph of the following function. The function we're given here is y equals square root 4f of x plus 3. Now the first thing I'm going to do with this is identify the parameters of this equation. So remember that this equation is in the form y equals square root a f of b x plus h plus k on the outside of the square root. So the a value here is 4, the b value is 1, the h value is negative 3, and the k value is 0. Now that I've identified the parameters of the question, I'll describe the transformations that I've covered. When describing transformations, we'll look for stretches, then reflections, then transformations, in that order. So, first what I can see is a vertical stretch by a factor of square root 4 about the x-axis. There are no other stretches present, so you can move on to reflections. There's no reflections present in this equation, so we can move on to translations. There's a horizontal translation 3 units to the left here. So that's all the transformations that have occurred on this equation. In mapping notation, the point xy turns into the point x minus 3 and square root 4y. Now that we've figured out what transformations have occurred, we'll apply them to the point negative 24 and 12. First, we'll apply the horizontal translation, which turns the negative 24 into negative 24 minus 3, which ends up being negative 27 over 12. Now we'll apply the vertical stretch by a factor of square root 4, which affects the 12 value here. It turns 12 into square root 4 times 12, which becomes square root 48. Square root 48 can be further simplified into square root 16 times square root 3. Square root of 16 is 4, and square root of 3 we can keep as is to keep simple, meaning the final point is negative 27 and 4 root 3. So when we're writing down the final answer, negative 27, 4 root 3 is a point on the graph y equals square root 4 f of x plus 3.